Hello, everyone. Okay, now this is section 1.4 and 1.5. I'll combine two sections in one lecture. So first I'll start 1.4, which is about polynomial function and also rational function. So let's start first with the polynomial function. So here on the screen, you can see that the polynomial function, this is a definition. Basically, you can write polynomial function in this form. All right, so and if you see here on the top, you see n, right? So this n must be a whole number. So let's see an example. So let's say if we have something like this, let's say a function where we write, let's say 3x to the power 7 plus 2x to the power, let's say 4. Let's just write random equation, 3x plus 2, something like this. This one is a rational function because if you see here on the top, the n, and these are all whole numbers, right? So as long as this thing on the top are whole numbers, even here on the top, we don't write anything that's 1, right? So even 1 is whole number. So yeah, if you have something like this, then we say this is a polynomial. So let's say if we have f of x is equals to 3 times x to the power 1 over 2 plus 5 times x to the power 5 x to the power, I don't know, let's say 4 over 7 plus 2x plus 8, something like this. So now here, in this case, now we have a power 1 over 2. Here, 1, 4 over 7. So these are not a whole number, right? So in this case, this kind of equation is not a polynomial, and here, this one is a polynomial. All right. And if it is a polynomial, then, so we said that this is a polynomial, right? So if it is a polynomial, then we can find two things, degree and leading coefficient. So the degree, we say the degree is the highest power of the polynomial. So the highest power here, if you see here, the highest power we see is 7, right? So the 7 is the degree. All right, this 7 is the degree of this whole polynomial. And the leading coefficient, we say the leading coefficient of this polynomial is the coefficient of the terms which has the highest power. So here, this term has the highest power, 7, so the leading coefficient is 3. All right, clear? So now here, in this case, since we said that the second function is not a polynomial, so we cannot find degree and leading coefficient. So that's not possible. So the only time we can find leading coefficient and degree is if a polynomial is, if a function is a polynomial. All right. Now, so so polynomial, the graph of the polynomial is always a continuous function. It might be something like this, or I don't know, maybe something like this, or maybe something like this, whatever. So what we can see from this is all of these functions are a continuous function, right? Because there is no break. It is going continuously, right? So we can say that the polynomial functions are continuous. And also we can see that the polynomial function, well, from polynomial function, if any of the polynomial function crosses at x-axis, then these points we call x-intercept point, right? So here it intercepts somewhere down there, something like that. All right, so yeah, the polynomial function is a continuous function. Well, also an example, even a function is a continuous, it is not a polynomial. So let's say, well, I said first, let me just write this. This is x-intercept. So now let's see example where we have, let's say, something like this. Okay, so here at this point right here, there is a sharp edge. So if a function has a sharp edge, even though this is it's a continuous function, right? But it has a sharp edge right here. So in this case, it's not a polynomial. All right. As I said here, that a polynomial must be continuous, but even though this function is continuous, we said this is not a polynomial because it has a sharp edge. But what about this function? Let's say, and we're not including this point, so let's say open circle, and again from here, we are not including this point, and the phone graph is going to look something like this. So is this a polynomial or not? Well, as I said that the polynomial here must be continuous, so we can easily see that there is a break right here. So from left to right, the graph is coming to this point, and there is an open circle here, so that means we are not including this point, and there is a big jump here, right? There is a jump here. See a jump right there. So yeah, so we can easily see that this is not a continuous function, so this is not a polynomial. All right. Now we can let's see some nature of, or some kind of properties of a polynomial graph. So now let's say if we have a graph something like this, right? Something like this. Here we can see, well, if you see a y-axis, if you see this y-axis, here this graph is going towards the negative infinity, right? Because if you go down on y-axis, it's going towards negative infinity. So we can say that this on this side it's approaching towards negative. And here on this side, if you see this is going up on y-axis, so this is going towards positive side. So yeah, on the left-hand side, it's going towards negative. On the right-hand side, it's going towards positive. Then we can say this graph has odd degree, which means the function might be something like this. Odd degree means the highest degree is going to be odd number, let's say 3. Something like this. I'm just writing a random equation. So what I'm trying to say is the function is going to be odd degree. All right. And also in this case, it is going to cross x-axis at least once. Here, this graph crosses x-axis here, 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 so which is more than once. So we're saying at least, sorry, I was trying to say once, at least once. Oops. At least once, all right? So that means the graph might be, so the graph might be something like this as well. So if we have something like this as well, a straight line, so this is similar to this condition. On the left-hand side, it is approaching towards negative on y-axis, right? Y-axis, it is approaching towards negative, and on the right-hand side, it's approaching towards positive, right? So these two are similar conditions. So again, here we're gonna have odd degree as well, all right? Or maybe we might have something like this. Yeah, so at least, well, on this one also, it is going, on left-hand side, it's going towards negative, on right-hand side, it's going towards positive. So again, this one's gonna have these properties, odd degree and crosses x-axis at least once, all right? The next one will be on both sides, it is going towards plus, right? Because on left-hand side, it is also going towards plus on y-axis, and also it is going towards positive side on y-axis, right? Because this is y-axis. Or we also might have something like this, right? On both sides, it's going towards positive, right? So here, the function, we're gonna have a function of even degree. So this kind of function, we say even degree function. And we also say maybe it's not going to, may not cross x-axis at all. So if you see here, this graph, it's not crossing x-axis, right? Because we have x-axis right here. It is not crossing x-axis, right? So it may not cross x-axis. That's what it is saying. And this one is going to have even degree. So maybe the function is going to look like, let's say, 3x to the power, I don't know, let's say 8 plus 2x to the power 7 plus 3. I'm just saying a random function. All right, so the function is going to maybe look like something like this, where it's going to have a degree even. So even degree means the highest power is 8. So that's why this is even degree. All right. So yeah, this is the idea of the polynomial. Now let's go to the next page. Now let's go to the next one, which is about a rational function. All right, so the rational function is something like this, where we can say a numerator on the top, n of x. So n of x is a polynomial. Polynomial divided by another polynomial. Let's say d of x. So n of x, or numerator on the top, that's why I'm saying n, and denominator d, d of x. So both of these, both n of x and d of x are polynomial. And the d of x on the denominator is not equals to 0. And the reason for that is, if you divide anything by a 0, is always undefined, right? So that's why the denominator must be non-zero. All right. So okay, now let's do an example here. So let's say we have a function given, or a rational function given. On the top, we have some polynomials. Let's say, okay, we have a polynomial, something like this: 3x squared plus 3x over 6 divided by 2x squared minus 2. Okay, now we need to find first domain. Second, we need to find x-intercept and y-intercept both. This too, I'm not going to do it now because I think I have already done similar problem the last chapter. So the domain for fraction, something like this, you have to look that the denominator is not equals to 0, solve for x and then get the domain. And for x-intercept and y-intercept, at x-intercept, we're going to assume y0, and at y-intercept, we're going to assume x0. Right, I did that in the last chapter, so you can follow that approach. What I am really doing here in this chapter is I'm going to talk about vertical asymptotes and horizontal asymptote. Sorry, this is number 4. All right, so again, this one I'm going to talk about horizontal asymptote and vertical asymptotes. So the idea, let's look at what does these two things means. The vertical asymptotes, let's see this in a graph. Let's say this is 2. Just draw a dotted line or vertical line that goes through this 2. And okay, now let's say we have a graph, something like this, which is approaching towards x-axis. Sorry, which is approaching towards this line, that the vertical line that goes through 2, but never gonna touch that line, this line. Similarly, from here, it is also approaching towards this line, but this is never going to touch this vertical line that goes through this too. So this graph is coming from left, right? So if it is coming from left, we said that x is approaching towards 2, right? Because this is approaching towards 2, because here this, when you see on the x-axis, it is approaching towards 2 from left-hand side. So if it is coming from left-hand side, we say a minus on the top or on the power. This defines that, okay, this graph is approaching towards 2 from left-hand side because of this minus. And for this one, now this graph is approaching towards 2 from right-hand side. So x is going towards 2 from right-hand side. So this case, we say plus on the top. All right, so this is how we define, or how we see whether the graph is coming from left-hand side or right-hand side. All right, so in this case now, since, well, both of these are approaching towards 2, but this is never touching this this line, right? This vertical line that goes through that goes through 2. So this is, we say this is, well, we know this is x is equals to 2 line, right? So this line, vertical line that goes through this point right here. So we say this line is x is equals to 2 line, and we say this is a vertical asymptotes. All right, so yeah, the reason is, yeah, this graph is never touching this line, and also this graph is never touching this line. So that's why this vertical line, we say this is a vertical asymptotes. All right. Okay, so now also now here we can see that if x approaches towards negative, so 2 to the power negative. So if this line approaches towards this graph approaches towards negative to the 2 to the power negative, then what about y? What is y approaching? So here, when you see this line approaching towards 2 from the left, then on y-axis, it's going towards negative infinity, right? So this is going towards negative infinity, because when this is going down on y-axis, it's going towards negative infinity, right? On y-axis, when you go down, it's negative infinity. When you go up, it's a positive infinity, right? Similarly, if x goes towards 2 to the power plus, then y approaches. So here now, if x is going towards 2 from right hand side, then y is, so this line or this graph is going up, which means y is approaching towards infinity. All right. So yeah, this is the idea we need to know. And this is the idea related to vertical asymptotes. Okay, now the next one is horizontal asymptotes, which is similar to vertical asymptotes. So once you know the idea of the vertical asymptotes, it's the same thing pretty much. So for the horizontal asymptotes, now we're going to have horizontal line. All right, so now let's say a horizontal line that goes through, let's say this point is 2, and we have another graph, something like this, which is actually, so this one is not going to touch this line, this horizontal line. It's approaching towards this line, but it's never touched this line. All right. Similarly, here we have same thing here. Again, this line is also coming from upwards, and yeah, it's actually going towards 2, but it's never going to touch 2. All right. So yeah, again, this one now, since this is a vertical line, so this line we say y is equals to 2 line, and this one is, we said this is a horizontal asymptotes line. All right, so similar idea like the vertical asymptotes. So horizontal asymptotes, here we can have horizontal line, and for the vertical asymptotes, here we have a vertical line. All right, so this is how we see vertical and horizontal asymptotes in a graph. Now, you will be asked maybe something, let's say something like, okay, I already asked you, sorry, I already asked you here. I'm sorry, I forgot that. So here, yeah, we have a problem here, right? So this is a problem, and we need to find the vertical asymptotes and horizontal asymptotes of this line. All right, so now to do that, well, first we need to look at the numerator. The numerator we have is 3x squared plus 3x minus 6. Okay, this is what we have in the numerator, 3x squared plus 3x minus 6. So basically we need to combine, or we need to simplify numerator and denominator. So the way we can simplify numerator and denominator is, let's factor this thing, or find the factor of numerator first, and then find the factor of denominator, and see if we can cancel out something. All right, so first numerator, we can see that we have 3 here, 3 here, 6 here, so that means I can factor out 3. I have x squared plus x minus 6. All right, so sorry, this is 2. 2. So then here we have 2 here, so that means I can say 2 times 1 is 2. So I have negative, so I can say here I get x plus 2, plus 2, and x minus 1 will give positive x, right? So yeah. Okay, so these are the factors of the numerator. Similarly, for denominator, 2x squared minus 2. First we can factor out 2. We have x squared minus 1. So we can also factor out x squared minus 1. We have a formula, a squared minus b squared is a plus b, and a minus b. So 1, we can also write 1 square, right? So that means I can use this formula. So x minus 1 times x plus 1. So now this is a numerator, this is denominator. Now I can combine these two because we have that f of x function. So f of x is equals to, on the numerator I have 3 times x plus 2, x minus 1 over 2 times x minus 1 times x plus 1. So now I can cancel out these two, so I get so now for vertical asymptotes, so for vertical asymptotes, we have to simplify this, right? So once you simplify this for vertical asymptotes, once you simplify this, after we simplify, we just have to look at the denominator part. So we have to look at the denominator part, and we have to make sure that the denominator, or we say that denominator is equals to 0, and say solve for this. So x is equals to -1. So this one is, we say this is a vertical asymptotes. All right, so first, the idea to find the vertical asymptotes is like I did here, simplify numerator and denominator, see if we can cancel anything like I did here. So I cancel these two, and then after that, look at the denominator and set that equals to 0, and solve for x. So that this thing is, we say this is a vertical asymptotes. All right, now for horizontal asymptotes, it's slightly different. For horizontal asymptotes, let me use black color. For horizontal asymptote, well, what we need to know is we need to know the degree. So there are like 3 cases. So first case is if I have a degree of numerator is less than the degree of denominator, then we say the vertical asymptotes is always y is equals to 0. All right, this is one case. Another case is, now let's say if the degree of now denominator is, now let's say if it is greater than the degree of denominator. If the degree of numerator, sorry, degree of numerator is greater than the degree of denominator. So in this case, we have no horizontal asymptotes. Let's just say no HA means horizontal asymptotes. All right. Now a third case is, now if we have a degree of numerator and the degree of denominator same, then we say y is equals to leading coefficient, or let me just say LC, leading coefficient of numerator divided by leading coefficient of denominator. All right, so we have these three cases. So since we have a function, let's go back. Okay, our original equation was this, right? So let me write that again. Okay, so our original equation, let me write that here again. F of x is equals to 3x squared plus 3x minus 6 over 2x squared minus 6, right? So here, when you see the original equation for horizontal asymptotes, if we have the degree of the numerator and the degree of the denominator same, then we use this, right? So here, if you see our conditions, the degree of the numerator here is 2, right? Because the highest power of the numerator is 2. And also the highest power of the denominator is also, it's 2. So that means these two are equal, right? So if we have degree of the numerator and degree of the denominator same, then the horizontal asymptotes are HA is y is equals to leading coefficient of numerator. So the leading coefficient of the numerator is 3, because the coefficient of the terms of the highest power is 3 divided by the leading coefficient of the denominator is 2. So yeah, this is the horizontal asymptotes of this function. There you go. All right, so yeah, this is the idea. So this is the idea you follow always to find the horizontal vertical asymptotes. All right, so for horizontal asymptotes, you have to look at the original equation and follow this approach. For vertical asymptotes, you have to simplify if it is possible to simplify. And then after you simplify, you look at the denominator and set that equals to 0 and find the value of x, and that or find the equation at the end. So x is equals to whatever you get. That's the vertical asymptotes. All right, clear? Now 1.5. This is, well, I think I'll finish it at this section. I don't think I will take too long. Exponential function. So exponential function, we say exponential function is something like this. Y is equals to a number on the base b to the power x. All right, so this number on the base, there is some conditions. So this number on the base must be greater than equals to 0. All right, so if this b on the base is negative, then it is not an exponential function. And also the b cannot be 1. So b is not equals to 1. So this means y is equals to, so as I said, that the exponential function should be in this form. So 2 to the power x, well, yeah, this is an exponential function because I have 2 on the base, a variable on the power, which is greater than 0, and this is also not equals to 1. So this is an exponential function. Similarly, if I say, I don't know, y is equals to 1 to the power x, is this an exponential function? No, because as I said that the b cannot be 1, so we have 1, so this is not an exponential function, right? What about y is equals to 1/2 to the power x? Is this an exponential function or not? Well, this is an exponential function because I said that the b, as long as the b is greater than 0, then this is an exponential function. So this is greater than 0, right? 1/2 is of course greater than 0. Y is equals to -5 to the power x. Is this an exponential function? No, because this base is a negative number, so this is not an exponential function. All right, now let's look at the graph of an exponential function. So the graph of an exponential function, when I say a graph, I'm talking about the shape, all right? The shape of the graph here of an exponential function is always like this. From left to right, it is increasing. So when you notice our present situation, the COVID virus situation, you can see the graph is similar to this. When we came to, like, I don't remember, I think it was around February, the cases increases rapidly, right? First, it was a constant, but within like 10 or 15 days, it increases rapidly. So yeah, present situation, when you compare the present situation, the graph is going to look something like this. So this is where the exponential function is useful. Okay, so here, this function, this graph is, well, it is when b is greater than 1. So we said that the b cannot be 1 and b must be greater than 0. But here, this is only possible when from left to right, if it is increasing, then we're going to have always a exponential function shape is always like this. That goes through. This is always 0, come on. All right. Doesn't matter. So the equation might be y is equals to 2 to the power x, as long as b is greater than 1. Y is equals to, I don't know, 10 to the power x. The shape, I'm just talking about the shape. The shape of the graph is always like this. Or maybe y is equals to 1 billion to the power x. All right, so yeah, as long as b is greater than 1, it's always like that. And if b is greater than 0 and less than 1, so if b is greater than 0 and less than 1, then the graph is decreasing. All right, so which is y is equals to 1/3 to the power x. Y is equals to, I don't know, as long as base is in this range, 2 to the power 7 to the power x. So in this case, the graph is decreasing. And this is what we are looking for in the current situation. We want to find a graph something like this where the COVID virus cases goes in like this, right? Okay, anyway, now let's go to the next page and let's solve an exponential function. So let's say 5 to the power x is equals to 25. Simple equation, right? So here, when you try to solve something like this, 5 to the power x is equals to 25, then well, we can use a property a to the power is equals to a to the power n. As long as the base are same, then we can say even, so we can say even the power is same. All right. So here, if we can make base same, then we can easily find the value of x, right? So 5 to the power x is equals to 25. We can say 5 to the power 2, right? So that means I can say x is equals to 2. Next example, let's say 3 to the power x squared is equals to 3 to the power negative x plus 6. So here we already have the base same, so I can easily say the power is also same. So x squared is equals to negative x plus 6. Then I can move both of these to other side, basically 8x, and subtract 6 on both sides, 8x and subtract 6. So on right hand side, these two are gone. So we get, left hand side, we get x squared plus x minus 6 is equals to 0. All right, so here we have plus x and we have negative 6. So I can say x plus 3 and x minus 2, right? Because plus 3 and minus 2 will give plus 1 or 1x. So this is algebra. But you guys must have done this in algebra, all right? So if you haven't done it, go back and review this. If you guys still have any questions, you can always ask me on the office hour, but it should be a simple math. Okay, now after this, okay, here you get the value of x, right? One is x is equals to negative 3. One is x is equals to positive 2. There you go. All right, so yeah, this is it for this section 1.5. So today I covered 1.5, so 1.4 and 1.5, right? So I think I have mentioned this in the email as well. So the quiz will be Friday, which will be over from section 1.1 to 1.5. All right. And so yeah, please watch all the videos I have uploaded so far. It will be exactly similar to the examples or ideas, similar to the example or ideas I mentioned on the lecture. So if you watch my lecture videos, it shouldn't be too hard. I will upload a quiz on the Blackboard, and I will ask you to upload your solutions again to the Blackboard and a PDF file, PDF file. So I have probably emailed this to everyone about this. So I hope everyone is checking my emails and everyone is watching or following the announcement and everything in the Blackboard. All right, so yeah, be safe, study hard. I'll see you in the next video. Thank you.